Wow. We have this double summation, and we have this improper integral from 0 to infinity, and we have a reasonably complicated expression inside. So how can we simplify this? And as we're about to find out, there are many different ways of approaching this. The first way is to evaluate the integral first. So integral first, so that may be the way you chose to do it, just the way it's stated. Or the second way is to switch the summation and the integral. Switch sum and integral, and by switching them, I mean placing the summation inside and putting the integral right outside, so switching their placement. And also, if you're doing it by evaluating the integral first, there are multiple different methods you can employ. You can either integrate by parts to evaluate the integral, so integrate by parts, or you may realize that this integral has a close connection with a Laplace transform, specifically t to the nth power, Laplace transform. Or you may realize that this integral also looks very similar to a gamma function, and it does not matter which way you employ. Of course, Laplace and gamma are going to be quite a bit faster than direct integration by parts, but integration by parts is not too slow either. But before we begin, I want to recognize Mohamed S. Fawzy for being the very first person to correctly answer this challenge question with the answer of 1. A huge shout out to Mohamed S. Fawzy. And in this video, I'm going to explain both solutions, and for the first solution, I will also elaborate on all three cases. Anyway, let's get started. So let's get started with the method where we integrate first, and I'm going to start by showing you the method using integration by parts. So let's focus our attention on this integral and realize that b factorial is independent of x, so you can bring that outside. So really, the integral that we care about is integral from 0 to infinity of x to the b power over e to the ax, or x to the b power times e to the negative ax dx. And if we integrate this by parts, letting our u be x to the b power and letting our dv be e to the negative x dx, so I'm using di method for integration by parts, and when we differentiate x to the b, we get b times x to the b minus 1 power, and when we integrate e to the negative ax, we get negative 1 over a times e to the negative ax, and of course the signs alternate, so plus then minus. And we see that this integral, using integration by parts, is x to the b power times negative 1 over a times e to the negative ax. So let me write that down. And we are integrating from 0 to infinity. And we have minus minus, so plus b over a times integral from 0 to infinity of x to the b minus 1 power, x to the b minus 1 times e to the negative ax dx. And we see that because e to the negative ax approaches 0 as x approaches infinity, because a is a positive integer, a is going from 2 to infinity, so this entire expression is going to evaluate to 0 as x approaches infinity, and when x is 0, x to the b is of course going to be 0, so this entire thing is going to be 0. So we have this integral being b over a times this integral, and as we can see, we have the same integral except that our exponent is being reduced by 1. So one way of thinking about this is that when we integrate this thing, our exponent is going to go down by 1, and this exponent is going to come out, and we are going to be dividing by factor of a. And we can apply that again to this integral. So when we apply the same integration by parts, we're going to get b over a is going to stay the same, and when we integrate this, same reasoning, b minus 1 comes out, so b minus 1 comes out, we are going to be dividing by another factor of a, and we are going to have integral from 0 to infinity of x to the b minus 2 times e to the negative ax dx, and we can apply it again to this one, and you get the point. We can apply it b times, So we can apply it again and again and again until we have a b times b minus 1 times b minus 2 all the way to 1. So we have a b factorial, and we have taken out b's, so a to the b power, and the function we have left is integral from 0 to infinity of x to the 0 times e to the negative ax dx. So I'm basically applying this integration by parts b times. When we do it once, b comes out, divide by a, our exponent is b minus 1, do it again, exponent comes out, divide by a, our exponent is b minus 2, and we're doing it all the way till our exponent is reduced to b minus b. And we see that integral from 0 to infinity of e to the negative ax dx, that's easy to evaluate. Anti-differentiating gets us negative 1 over a e to the negative ax, and going from 0 to infinity gets us simply 1 over a. So this entire integral turns out to be b factorial over a to the b plus 1 power. So keeping that in mind, let's go back up. So we know that this entire integral, except the b factorial part, is going to be b factorial over a to the b plus 1, and of course we have to divide by a factor of b factorial. They are going to cancel out, so we see that this entire integral is simply 1 over a to the b plus 1 power. And as I previously mentioned, there are two other ways of evaluating this integral, and they are Laplace transform and gamma function. So let's quickly touch on them before moving on. So I'm going to focus on this integral once again. So the integral that we get when we take b factorial outside. So I copied the integral right here, and if you look at it closely, if you have taken differential equations in college, you may recognize that this integral looks exactly the same as Laplace transform of t to the nth power, where n is an integer greater than or equal to 0. And of course, by definition, Laplace transform of t to the nth power is integral from 0 to infinity of t to the nth power times e to the negative st dt, and this is n factorial over s to the n plus 1 power. And we see that our integral looks the same. Instead of t, we have x, and instead of n, we have b, and instead of s, we have a, but these two are identical. So we know our integral has to be b factorial, n is b, over s. In this case, s is a to the n plus 1 power, and in our case, our n is b, so b plus 1 power, and we get the same result. And of course, as you can tell, to derive that this Laplace transform is n factorial over s to the n plus 1 power, you can use the same method that we showed. So using this integration by parts, you can actually show, in fact, we have shown that this Laplace transform evaluates to n factorial over s to the n plus 1. But if you have taken differential equations, you may have this memorized, or you may have a table with this written explicitly on it. So you can really bypass the cumbersome integration by parts and find the answer right away. Anyway, so that's another way if you saw it as Laplace transform. And finally, using gamma function. So let me go down once again and define gamma function for those who've never seen it before. Gamma function of t is defined to be integral from 0 to infinity of u to the t minus 1 times e to the negative u du, and it can be shown using the same integration by parts method that this entire thing is equal to t minus 1 factorial for t greater than or equal to 1. And of course, I'm talking about integer values of t. And we see that we have something very similar to gamma function. Instead of negative variable, we have negative a times variable, but you can change that right away. You can make the substitution u equals to ax, or du is a dx. And using the substitution, we get integral from 0 to infinity. The bounds stay the same. And we have x being u over a, so u to the b over a to the b, times e to the negative u, and du is a dx, so dx is du over a, so dividing by another a, and we have 1 over a times b plus 1 times integral from 0 to infinity of u to the b times e to the negative u du, and as we can see, that is gamma function evaluated at t equals to b plus 1. So we know that's b plus 1 minus 1 factorial or b factorial. So this entire integral evaluates to b factorial, and we get the same thing. So let's go back up, and once again, gamma function and Laplace transform really have this integration by parts programmed inside. So really, you're just skipping a step. Anyway, let's finish the problem. So we know this entire integral evaluates to 1 over a times b plus 1 power when we divide by b factorial. So now let's focus on the summation. So let's focus on the summation from b equals to 1 to infinity of 1 over a to the b plus 1 power. Well, that is, when b is 1, we get 1 over a squared. When b is 2, we have 1 over a cubed. Then 1 over a to the 4th. That's infinite geometric sequence with common ratio 1 over a. So common ratio is 1 over a, and because a is ranging from 2 to infinity, the absolute value of the common ratio is less than 1. So we have a convergent geometric series which evaluates to first term over 1 minus the common ratio, and simplifying this gets us 1 over a squared minus a multiplying by a squared to top and bottom, and that's of course 1 over a times a minus 1. So we know this entire thing is 1 over a times a minus 1, so all we have left to do is to sum that from a equals to 2 to infinity. So let's go down. So we want to sum a equals to 2 to infinity of 1 over a times a minus 1, and this looks like a classic telescoping sum. So let's break apart 1 over a times a minus 1, so a equals to 2 to infinity. You can either find the partial fraction decomposition, but really in this case it's pretty obvious that this entire thing is 1 over a minus 1 minus 1 over a. And when we evaluate the summation, we are going to have 1 over 1 minus 1 over 2 when a is 2, plus 1 over 2 minus 1 over 3 when a is 3, plus 1 over 3 minus 1 over 4, all the way. If we are stopping at some value n, we're going to go all the way to plus 1 over n minus 1 minus 1 over n. And of course, all of the middle values are going to telescope out of it. All of them are going to cancel out. And as n approaches infinity, this is going to approach 0. So in the end, the only term we are going to have left is 1. So this entire double summation and integral evaluates to 1. So that's one way of doing it. And if you're doing it by gamma function or Laplace, it's actually a pretty fast way of doing it too. But now let me show you the second way, where we switch the summation and integral. Now the first question you may ask is, are we allowed to switch the summation and the integral in this case? Because it's not allowed in every single case. But in our case, we can, because our function inside is always going to be greater than or equal to 0 for all values of x and b that we care about. And it can be proven using real analysis that when the function inside is always greater than or equal to 0, you can interchange sum and integral without causing any mishaps. And in our case, because b is positive and x is ranging from 0 to infinity, our function inside is obviously going to be greater than or equal to 0 for our values of b and x, so we can safely switch the summation and the integral. And when we switch them, we are going to have integral from 0 to infinity, summation from b equals to 1 to infinity of x to the b power over e to the ax times b factorial dx. And from here, because a is independent of b, we can bring this e to the ax outside the summation. So we get integral from 0 to infinity of 1 over e to the ax times summation from b equals to 1 to infinity of x to the b over b factorial dx. And we realize that this entire thing, it looks very similar to Taylor series expansion of e to the x. You may recognize e to the x is summation from b equals to 0 to infinity of x to the b over b factorial. But in our case, we have the same thing, except that we're starting at b equals to 1 instead of b equals to 0. So this entire thing is simply e to the x minus 1, because when b is 0, this entire thing becomes 1. So all we have to do is integrate this, and this is integral from 0 to infinity of e to the negative x times a minus 1 minus e to the negative ax dx. I'm just distributing this. When you distribute like this, you have e to the negative ax and e to the x. And when you distribute it to negative 1, you are of course going to get e to the negative ax. And when we anti-differentiate this, we get negative e to the negative x times a minus 1 over a minus 1 minus 1 over a e to the negative ax. Go from 0 to infinity, and you're going to get 1 over a minus 1 minus 1 over a. So we are going to be summing up 1 over a minus 1 minus 1 over a, and that's the same thing we had before. So from here, you do the telescoping sum once again, and we are going to get 1. So that's probably the fastest way of approaching this question. But I hope that every single method was to some extent educational and informative, but above all, I hope you enjoyed this video. Anyway, the final answer to this question is simply 1.